Welcome to EDU World Space.
Alright guys, we're doing problem 104 of chapter 9 in Chemistry Essential Science. So the highest occupied molecular orbital of a molecule is abbreviated as the HOMO. The lowest unoccupied molecular orbital in a molecule is called LUMO. Experimentally, one can measure the difference in energy between the HOMO and LUMO by taking electronic absorption, the UV visible spectrum of the molecule. Peaks in the electronic absorption can be labeled as pi to p to anti-pi to p, or sigma to s to anti-sigma to s, and so on, corresponding to electrons being promoted from one orbital to another. The HOMO-LUMO transition corresponds to molecules going from the ground state to their first excited state. Write out the molecular orbital valence electron configuration for the ground state and first excited state of N2. We have that here. On the left, you see N2. On the right, you see N2 excited. So is N2 paramagnetic or diamagnetic in its excited state? And remember, paramagnetic means you have unpaired electrons in your molecular orbital. Diamagnetic means there are no unpaired electrons in the molecular orbital. And as you can see, you do have unpaired electrons in your molecular orbitals, in your sigma and anti-sigma orbital. So that's going to be diamagnetic. So see, the first electronic absorption of the N2 molecule has the lowest energy peak at 170 nanometers. To which absorption transition does this correspond? If that's the lowest energy peak, that means it's going to be the conversion from the HOMO to the LUMO. So that's going to be, so our HOMO is going to be our sigma orbital, and our LUMO is going to be our anti-sigma orbital. So that corresponds to our sigma to anti-sigma transition. Because that's going to produce the smallest gap in energy. So so calculate the energy of the HOMO-LUMO transition in terms of kilojoules per mole. So let me see if I can shrink this. So we want to we're going to do E is equal to N, which is Avogadro's number, H C over lambda. And lambda is going to be 170 nanometers. C is speed of light, H is Planck's constant. So E is equal to 6.02 times 10 to the 23rd inverse moles times 6.63 times 10 to the negative 34 joule seconds times 3 times 10 to the 8th meters per second over 170 times 10 to the negative 9 meters. And I'm just going to convert this to kilojoules right off the bat. Times 1 kilojoule per 1,000 joules. So E is going to equal times 6.02 times 6.63 times 10 to the negative 34, or times 3 times 10 to the 8 divided by 170 times 10 to the negative 9 divided by 1000. So E is going to equal 704.34 kilojoules per mole. So that's going to be the energy of the HOMO-LUMO transition. Now, part E. Is the NN bonding in the first excited state stronger or weaker than in the ground state? So let's look. In the ground state, we have electrons filling our sigma above our pi orbital, so we have a triple bond. Now, in our excited state, we have electrons in our pi orbitals, and we have one electron in our sigma orbital and one electron in our anti-sigma orbital. So by definition, since we have electrons in our anti-sigma, our electron is moving from our bonding orbital to an anti-bonding orbital. So first of all, taking away an electron from your bonding orbital will, by definition, make it less stable. The more electrons you have in your bonding orbital, the more stable your bond is. Secondly, putting them in your anti-bonding orbital will further destabilize your bond, because putting electrons in your anti-bonding orbital makes your molecule significantly less stable because the anti-bonding orbitals are higher in energy. So the NN bond is weaker in the first excited state compared to our ground state.